let's talk about mechanical energy. What is it? When is it conserved? And I'll show you an example of a mechanical energy system with the pendulum, a swinging pendulum. Now, what is mechanical energy? Well, mechanical energy, okay, by definition is, well, we use the letter E to represent mechanical energy, and it is the sum of these three kinds of energy: kinetic plus gravitational potential energy, that is the energy stored up in an object because it has height above the ground or some reference level, plus any elastic energy it has. If maybe something is sitting on a spring that's been compressed, that spring can be released and push on the object and can release its energy into the object. So when I look at an object and I say, okay, how much kinetic energy does it have? How much gravitational potential energy does it have? How much elastic potential energy, it might have? We're not really going to deal with this one today. But this is the definition of what mechanical energy is. And we use a capital E to represent mechanical energy. There are lots of other kinds of energies that we've been talking about, forms, ways of storing energy. We can store energy in the way molecules are arranged. That's chemical potential energy, but that's not part of our definition of a mechanical energy. You can also store up energy in the motion of the molecules, okay, in the temperature of an object. Obviously, if you have boiling water, that boiling water can make changes to its environment, right? Okay, stick your hand in a vat of boiling water and you will notice that there is a change to the environment of your hand, a catastrophic change. Okay, so don't do that, okay? Kids, don't do this at home. But the energy associated with temperature is not included in this definition. Strictly kinetic potential and elastic potential, gravitational potential and elastic potential energy. That's it. Okay. Now, when is this quantity of energy, this mechanical energy, conserved? I'm going to show you a very, very simple example of it. And then we'll go talk about the pendulum. Let's take a look at, here's the ground, and here's like a ball, like a baseball, held above the ground, and it's motionless. Okay? Which means it has what energy? What kind of energy does it have if it's not moving but held above the ground? Yeah, it has potential energy. So if you say, well, its kinetic energy is just 0. It does have gravitational potential energy, and what is that? M, the mass of the ball, times gravity, times height. And, of course, there's no springs or anything here, so it doesn't have any elastic potential energy, so that's going to be, so U sub E is going to be 0. So all of its mechanical energy in this case is in its gravitational potential energy. But then you release the ball. And now work is going to be done. Now take a look at this. Gravity, this is the force of gravity. And let's say it fell down a certain displacement. This is our delta y. Do you see that the force and the displacement are in the same direction? Right? And so gravity is doing work. So the gravity that's doing work, well, do you see that gravity is the net force? It's the only force acting on the ball. So the work done by the net force will be equal to the change in kinetic energy of the ball. Well, the work done by gravity here is just the force times the delta y times the cosine of the angle between them, but that angle is 0, down and down. The angle between down and down is 0, and the cosine of 0 is 1. So we don't need to worry about the angle. And that's going to be equal to the change in kinetic energy, which is going to be K final minus K initial. But what was, let me zoom in because I'm writing too small. But what is the initial kinetic energy of this ball? It's 0. Now, this right here is the work done by gravity, and the work done by gravity results in the change of kinetic energy. But look what I've done if I fall down. If my delta y is negative, if I fall down, what am I doing to my height? I'm reducing my height by that much. If I reduce my height by that much, what have I done? If I've reduced my height, I have reduced my gravitational potential energy. So, in other words, the work done by gravity, this is the work done by gravity. If the work done by gravity is positive, I've gained kinetic energy, but I've lost gravitational potential energy. So the way to look at this, like with the bar charts we were talking about, the ball started off with this much gravitational potential energy. And then gravity did work. And when gravity does work, that energy, that means gravity is saying, hey, I'm going to give you energy. I'm doing work, I'm doing positive work on the ball. I'm doing positive work because the force and displacement are in the same direction. So I'm going to give you kinetic energy, but somebody's got to pay the price. That energy has to come from somewhere, and where does it come from? It comes from the gravitational potential energy the ball had to begin with. So when gravity does positive work, it takes energy out of, it comes at the cost of my gravitational potential energy and transfers in to my kinetic energy. Now let's suppose we're about halfway down. Let's look at the ball. It's about halfway down, which means I've lost half of my gravitational potential energy. But the work done by gravity, that's exactly equal to the amount of potential energy I lost and exactly equal to the amount of kinetic energy I gained. So if I fill this up, that means I'm losing this as it pours out. And so that when you're halfway down, the energy is half and half. Okay? And so this is an example of when gravity does work, we take the energy out of gravitational potential energy and put it into kinetic energy. But do you see that I haven't lost or gained any energy? I've just changed how it's stored in the system. Well, so it's almost like, look, all I'm doing, if I look at my mechanical energy equation, all I'm doing is taking energy out of here and putting it into here. But what do they add up to? The same amount of energy. In other words, the energy is conserved. So this is when mechanical energy is conserved. And we're going to go over this many times in many different ways. So we're not done with this yet. But mechanical energy is conserved. That is, the total amount of the mechanical energy doesn't change when gravity, or when, hold on. Let me change this a little bit. When the only forces doing work are gravity and or springs. If a spring is doing work, all we're doing is transferring energy from the spring into one of these other two guys. When gravity is doing work, all we're doing is transferring energy from or to gravitational potential energy from kinetic or elastic potential energy. Okay? And if that is true, then the total amount of energy isn't changing. This is kind of similar to what we did with momentum. But instead of P initial equals P final, we write E initial equals E final. But this is only true. This equation right here is only true. You can only use it if the only forces doing work in your system are gravity and springs. Because then we're just transferring energy from gravitational potential energy to kinetic energy to elastic potential energy. But when you add them all up, you get the same thing. Now, the pendulum, oh, are you done with that? You all got that? Now, the example that I showed you earlier is a pendulum. When the pendulum is down here, okay, let's here's my nose. I'm wearing my glasses, okay. Okay, now that's pretty horrific. All right, but anyway, if let's say we lift this up, so somebody lifts this pendulum up, that means they did work on the system, and it was an applied force. It wasn't gravity doing the work. It wasn't a spring doing the work. It was somebody grabbing this thing and pulling this thing up. So they added energy to the system, right? But then they released it. Now let's take a look at the forces acting on this pendulum once it's released. You got the force of gravity, and you got a tension force like this. I'm not drawing this very well, but there's my tension force, and that's it. Now, the motion is in this direction, right? The motion is always, of this, is always tangential or perpendicular to this string. So the tension force never does any work. Why? Because it's always perpendicular to the direction of motion, and therefore doesn't do any work. But look at gravity. Gravity is going to have a component that is perpendicular. But that component's going to change depending on what this angle is. But gravity is doing the work when it pulls it down here. And so what we're doing, the only force doing work here is gravity. And it takes the gravitational potential energy and pours it into kinetic energy when it gets here. But then, of course, it goes through the person's face and then up this way, right? Let's say the person moves away. And that energy turns back into gravitational potential, and then back into kinetic, gravitational potential, kinetic, potential, kinetic, potential. And it swings back and forth, but the total mechanical energy in this system stays constant. And this will allow you to solve problems, and we'll work some examples next time.